Cool.
Also, uh, the recording of yesterday's meeting will be posted. I will send out an email detailing all the information. So this is what the schedule will look like for today. Uh, First of all, we'll have this presentation with Emma, and then I'll talk about using the Harvard Smithsonian Telescope and doing image processing with it. And then after that, we'll do the daily photo share. If everybody was able to take photos, take a few minutes to see who wants to share their photos. Then after that, I'll give a short Tinkercad tutorial, and then Hanson will and me will go present a project, which you guys will do 3:30 to 5. Yeah.
Great. So do you want Grace and I to take it with the presentation then? Yes? Okay.
I
Maybe she
yeah.
and I can do intros first and then we'll do our presentations. So hi everybody, my name is Dr. Emma Kane Loudon. I am the president of SLOOH. I am so excited to meet you all and to be with you today. My background is in astrophysics. I did my undergrad at Princeton and my PhD at Yale studying exoplanets. So I'm always been interested in studying planets outside the solar system and trying to understand how they form and evolve. So if you have questions about planets, I'm your person. I love talking about them and just yeah, it's really fun. So I grew up in Utah, fell in love with the night sky there, where I could see the Milky Way from my backyard, and have continued that passion for astronomy. And I'm really excited that all of you are on SLU and getting to explore that passion with all of us this week and beyond. Grace?
Hi everyone, my name is Grace Jackson. I am SLU's Director of Operations, and I have a different journey to the night sky. I grew up in cities. I could see maybe 10 stars in the night sky and didn't fall in love with astronomy until I arrived at my undergrad in Wellesley, Massachusetts, and had access to telescopes and had access to darker skies and absolutely loved it. But I, unlike Emma, did not go the PhD route and did not become a scientist. I became an engineer. I love thinking about how things work and how to help the wonderful scientists do the work they need to do to make wonderful discoveries. So I worked at NASA for 2 years, and now I'm here at SLU after getting my master's, and I'm excited to talk with all of y'all.
We're so excited to talk with all of you. Grace, do you want to go first or do you want me to go first? I don't have a preference.
I- I'm happy to go first.
Okay, go for it.
Okay, folks can see my screen, but maybe
Yes.
not me.
Yes.
Yes.
Okay, I can no longer see you. So today, like I said, I'm an engineer, and I wanted to talk about some different types of telescopes and how they work and where they are and all of that fun stuff. Um, I said a little bit of this in my introduction, but I was a city kid. I had no exposure to the night sky until I got to undergraduate. And I didn't even think I was going to be an astro major when I got to my undergraduate institution. I thought I was a political science major. I took one class and just absolutely fell in love. And so I'm so excited that y'all are finding it a little earlier than I did, and hopefully cultivating that love because it is just such a beautiful world to be exposed to. So there's a bunch of different types of telescopes, but I thought I would start sort of at the beginning. The first type of telescope that I ever used is a refracting telescope. So these are historic telescopes. This is the Great Refractor at Harvard. It sounds like y'all might talk about some of their more modern telescopes later today. But this telescope was installed in the 1800s. It is a 15-inch telescope, so we refer to telescopes based on their diameter, based on their size. But in order for the lensing to work, it has to be 20 feet long. So refracting telescopes use lenses, not unlike glasses. So the light comes in and is focused um, to have that magnifying effect. And the way this lensing works gets into trigonometry that we don't need to talk about today. But the sheer scale of these telescopes makes them pretty impractical. Flipping the telescope over the mount can take a lot of specific maneuvers and a lot of, in our case, like running and jumping with ropes to get enough momentum. Um, the domes are huge, and the way you take photos with these kinds of historic telescopes is basically film photography, but with glass plates. And so that's not super practical for modern research purposes either, which is why we now use reflecting telescopes. So instead of a lens focusing the light to have the magnifying effect, it uses two mirrors. So the light comes into the telescope, bounces off a primary mirror onto a secondary mirror, and then onto the eyepiece. These are the telescopes that SLOOH uses and are sort of a modern research standard. So this is a plane wave telescope that SLOOH uses, and the light comes in, bounces off the primary mirror onto the secondary mirror, and then into the eyepiece. Rather than being long and thin, they're sort of short and stout. These mirrors, the mirror diameter is what we use to measure it. So at SLOOH, we have half-meter telescopes, and the size of the primary mirror gives us the same magnification, but a similarly sized refracting telescope would need to be incredibly long. So a half meter is, half a yard, so a foot and a half, and that would need to be like a 30-foot long refractor. Whereas these are much more easy to manage. The domes can be smaller, and that makes it so that we can put them in more unique places with better seeing, less light pollution, and overall just makes it much more accessible to use. Now we have to talk about how we take all of the beautiful images from the telescopes and put them on a computer and save them as the photographs that you see on SLOOH. We use CCDs, which are charged coupled devices. These are chips made of silicon that are divided into many little pixels of light-sensitive cells that use the photoelectric effect to release electrons when they're struck by light. So looking at this diagram right here, these green dots are photons, little packets of light that hit our silicon, release electrons, and then this is translated into a grayscale image. We also use long exposures, so we can look at dark things. If you've ever, for example, like tried to take a picture of the sun and left the shutter of your camera open too long, it'll get overexposed. That light sort of takes over and floods the sensor, and we don't want that. So lots of things to consider in our CCDs, but that brings us to filtering. Hopefully y'all have used a filter, like maybe on Instagram, but filters are things that we put in front of a camera to make it so that only certain wavelengths of light can get through. We can see a spectrum of visible light, but there's lots of different types of light, and filters exist for all different types of light, no matter sort of what area of the spectrum they live on. So we get these grayscale images from the CCD, and they correspond to certain parts of the electromagnetic spectrum. And we use 3 of these grayscale images with different filters to stitch together and to make the color image that you see on SLOOH, or that you see from like the James Webb Space Telescope, which we'll talk about in a little bit. But the way that you put these different filters together can change how the image looks. It's sort of an artistic choice. Different telescopes will have slightly different filters, and different people will have slightly different post-processing, and you can learn a little bit more about that in some of our SLOOH quests. But it's really cool to be able to take a photo and then put your own spin on it. So each of these images are of the same object, the Crab Nebula, from different telescopes with different post-processing. You can see they have sort of the same shape and the same features, but not quite the same look. This last picture on the right is a composite image. So it's taken over several nights. It's taken with several different telescopes. You can get even more detail. You can see this image has way more stars than the other ones, and just a little more detail in the beautiful Crab Nebula. That was a lot of information that I threw at you. I wanted to take a brief pause if anyone had any questions. I'm very patient. I didn't mention that in my intro, but I will wait. Somebody has a question. I just threw very complex science at you for somewhere between 11 and 9 minutes. Are you sure?
You can ask or type in the text, ask questions.
I have one question. Can you go to the previous slide?
This one?
Yeah. So why does this telescope take a picture of different colors and different numbers of stars?
So the different numbers of stars is because the telescope exposures are different. So we talk about exposures and the amount of time that we're collecting light. So we open the telescope shutter and it lets a bunch of light in for like 30 seconds. And then you close the shutter. And the longer the exposure, the more light you let in, the more faint objects can be seen. But you don't want to leave the shutter open too long in exposure, because then, like I said, the sensors will get flooded and you just end up with a white blob instead of the beautiful detail that you can see in the nebula. And then the different colors are the different like sort of star forming regions. Emma will be better at talking about this than I am, to be honest. But the different star forming regions, the different gases that emit different color lights. I don't remember what kind of nebula the Crab Nebula is. Maybe Emma will. But
It's a supernova remnant.
it's a supernova remnant. Thank you so much. But it's just the different gases that emit different colors of light.
And you have a
Anyone
second
else
question
have
in
a
the chat.
question? Oh, we do?
Yes, are
Reflective
reflective
telescopes.
telescopes easier to build?
Thank you. I would say they're different to build. Optics were never my strong suit. The focusing on, to be honest, both types of telescopes are really, really precise. But they are definitely easier to use and easier to manage. And they're easier to repair. So I've done maintenance on reflective and refracting telescopes, and this the scale of the refracting telescopes can make it really challenging to get focusing changes correctly, to even just clean the lenses is really challenging. Whereas the reflecting telescopes that I maintained were much less complicated. Required a little bit less like Pilates moves to get in there and climb ladders and that kind of stuff. Awesome.
Real
Anything
quick,
else before I? Yeah.
real quick, couple of addendums to that last question. A refracting telescope, the glass has to be supported by the edge since the light's going through. A couple of things. One is that the glass has to be perfect. If there's any imperfections in the glass, it ruins the image. The other thing is it sags being supported by the edge. So the biggest refracting telescope is about 36 inches in diameter. Anything bigger than that, it sags too much and destroys the image. Whereas I think the biggest reflectings are 8 meters and up, so they're huge. And because they're supported from behind, they don't have problems. So the other thing is refractors produce color in their imaging because they're like prisms in a way. They have color fringes on the edges of bright objects. So reflectors don't have that. So a lot nicer telescope, especially for research.
Thank you. All right. So we talked about telescopes on the ground. We also have telescopes in space that are doing fantastic science. And I wanted to facilitate just like the questions in the chat or just shout them out. Like, what are some benefits to putting telescopes in space and what are some downsides to putting telescopes in space? Let's brainstorm. Yeah, you can go ahead. So in the chat, we have benefit of less light pollution, exactly. And you have no atmospheric issues. Seeing is a huge part of telescopes. So if you've ever looked across a hot road on a hot day, you can see those atmospheric disturbances. And looking through a bunch of atmosphere, they have those atmospheric disturbances. So we get rid of that issue for sure. Earthbound telescopes, Starlink, also an issue, even in the picture that I showed from Wellesley. The downsides is that you can't fix it easily. We sometimes go up and fix them. The Hubble Space Telescope had a servicing mission, but we'll talk about this in a little bit. But the Hubble Space Telescope is much closer to Earth than the modern space telescopes. Space debris is definitely a potential hazard, in particular in low Earth orbit. When I worked at NASA as a flight operations engineer, we did maneuvers about monthly to avoid debris in low Earth orbit. So it's definitely a problem. So Emma knows more about the Swift telescope deorbiting than I do. But I think it's mostly due to atmosphere and like a more active solar season than initially anticipated. But
It's also a really old mission, if you don't mind me chiming in. I'm
yeah,
really excited about what they're doing with Swift right now. It's a really old mission, so um, it was kind of a last-ditch effort to say, okay, what can we do to boost the orbit of this telescope? And they worked with a company called Catalyst Space, who built a docking mechanism that was launched last Friday on a Northrop Grumman rocket to go and dock with the Swift telescope and basically fire thrusters and boost the orbit a little bit and preserve the lifetime of the telescope. It's a huge engineering feat that's going to really help the scientists because it was a telescope that's not designed to be docked with. So it's a really kind of amazing test of will this work. Scientists want to keep the Swift telescope around because it's a really important part of the decadal survey, which is a way that astronomers try and figure out what are our priorities for the next decade. What Swift can do is a big part of those priorities, even though it's so old. So preserving it is really important, and it's a really cool public-private partnership between NASA and these private companies to see, can we fix this telescope with robotics?
I met Swift operators. They're based out of Penn State, is my recollection, but they came to my NASA center at Goddard, and they were talking about like they're sort of mourning the end of their mission 2 years ago when I met them, and now it's so cool that there's this sort of resurrection of the mission and it's going to get to live on because it is doing such cool science. All right, back to the topic at hand. So the Hubble Space Telescope, I mentioned it's in low Earth orbit, so it's relatively close to Earth. The primary mirror is 2.4 meters across. It's a reflecting telescope. So I said that SLOOHs were half meters. So this is about 5 times bigger than SLOOHs telescopes. It launched in 1990, which is crazy that it's approaching 40 years on orbit and has been just producing beautiful, beautiful images and wonderful science for basically, I mean, like my whole life for sure, um, which is fantastic. One of the things that I love about astronomy is the opportunity to sort of apply math as a way to model the universe. So I thought I would introduce just some like little tiny math problems. I geared them toward sort of like a seventh grade math level. So if y'all want to take 2 minutes and try these questions, the second one is just like if you are looking for a little extra challenge, um, a little estimation game, but 2 minutes and then we'll step through it. And if you have questions, please feel free to ask them.
Rivenson, do you have any question? You raise your hand.
All right.
Okay, so since I'm a third grader, I'm going to try it. I might know the answer.
Okay.
So, is it, what was it again? 3 hours. 8 times 483.
You're looking at the radius. What you want is the circumference of, let's just assume Earth is a circle. So then
Exactly. So we want to
what
look
we
at a
have is a
circumference
massive
rather
number.
than
It's like
Okay, that's the
what we
order.
have is 48556.45605 kilometers.
Alexander's correct.
Grace, you're muted, by the way. Grace.
You're muted.
Wait a second. Actually, you also need the radius of the Earth, I think. Yeah, I think you need the radius of the Earth to calculate this. Because what we have is the orbital radius.
Grace, you're muted.
You're muted.
You're muted.
Yeah, you're muted. You're muted.
You're muted.
You're muted.
Grace,
You're
you're
muted.
muted. You're muted.
You're muted.
You're muted.
You're muted.
You're muted.
Grace, I said you're muted.
Sorry, team. I muted myself to sneeze and then I forgot to tell you. I forgot to undo it. So the first step is always going to be to draw a picture for me when solving a problem. This can seem like a really simple, like a simple sort of geometry thought process, but it can be really easy when you draw a picture to see that I gave you an altitude of 4,000 or 483 kilometers, but that's not the full radius of the circle that we want to calculate. We have to calculate it from the center of the Earth. That's the radius of the circle. So it's a little bit larger than maybe you were expecting. And if anybody did the football fields question, it's like somewhere in the ballpark of 5,000, depending on the exact figures that you used. If you like did 100 yards or you included the end zones, that kind of stuff. The other telescope I wanted to talk about is the James Webb Telescope. It's another reflecting telescope, but it is Hubble's more modern successor. So it launched in 2021 on Christmas Day. Its primary mirror is 6.5 meters across, and it's made up of these little hexagons that actually have small actuators behind them. So scientists couldn't make a mirror that large that was sort of precise enough to
So it's like a whole bunch of
ensure that the
mirrors.
images would be pristine. And so they created instead all of these hexagons, this array of hexagons for the primary mirror. And as the telescope is focused, those hexagons can adjust just ever so slightly to provide a more accurate focus. I've been in the James Webb control room, and it is so cool. I'm not allowed to show you pictures. I would if I could, but each of those little actuators, the little motors to move the mirrors, can be controlled manually, so they can like wiggle a space telescope live. And then just a small note on James Webb's orbit. We talked about in sort of the pros and cons of space telescopes that they're harder to repair. James Webb is much farther away than Hubble is. It's 1.5 million kilometers away, and so it's
I think Lagrange
at this
L2.
special
It's
point
at
called
L2. I think
L2,
that's
and it would not be repairable. There was a lot of concern when James Webb launched. All of the mirrors were folded in this sort of origami like way, and then the mirrors were unfolded as part of the commissioning effort, and there was real concern that like the mirrors would not unfold and we would have this useless telescope 1.5 million kilometers away. But everything went perfectly. The James Webb images are stunning, and the science has been fantastic. There's also a new telescope that's going to head out to L2, hopefully in August, called the Nancy Grace Roman Telescope, which will be sort of Hubble's successor. It looks in the same wavelengths as Hubble, and has some different instruments that scientists are really excited about, including a super wide array camera that hopefully will provide even more beautiful images and even more fantastic science. I didn't advance the slides, but if I did, you would see this wonderful image. So this is a Hubble field of view, and this is the Nancy Grace Roman field of view. So it's the same resolution, but just a much wider field of view, so you can get even more panoramic shots. Like I said, Nancy Grace Roman is hopefully launching in August. It just arrived at Kennedy Space Center in Florida. It was built in Maryland at Goddard, and is if it launches in August, then we'll be commissioned sort of through the end of the year, and we'll have first light hopefully next winter, early spring. So with that, does anyone else have more questions before I hand it over to Emma?
No.
Awesome.
Alrighty. Thank you for the great presentation, Grace. Let's do some Zoom applause for her. Thank you, Grace. I am really excited to talk to you today and follow that incredible presentation. We're going to go from how you discover anything with telescopes and how the telescopes work to the people who are discovering and who have discovered objects through telescopes and what they learned and how they learned it. Before then, there's one question left over from your talk, I think, which is a question about what are actuators, if you want to answer that from the chat.
Such a good question. Actuators are little motors that we can control really precisely. But it's just a motor. It's just like what's ever worked with robotics, like just little um, levers that you can push with a motor.
Awesome. Cool. All right. I'm going to share my screen and we'll go through this next set of what is actually discovered. In the meantime, can everybody please put the name of your favorite astronomer in the chat? Let's see, how do I see the chat? There we go. Kepler, lots of Keplers. Kevin, I think Kevin's on the call. Copernicus, Galileo. All right, keep them coming. Herschel, I love Herschel. One of my dreams is to get a dog named Herschel. Two dogs, Kepler and Herschel. Those are my dog name dreams. One will be a lab and one will be a mini Bernedoodle, but that's beside the astronomy point. So I am really excited today to talk about some of the objects that you can look at on SLOOH later today and the people who have helped us learn a lot about them. So first up is the sun. The sun is about 8 light minutes away from us. We've all seen it in the sky. How many of
Yeah,
you
they're
have
small in
seen
appearance because of their great distance from us, but the real
somebody who's on the
problem
SLOOH
with
mission interface? Um, how many of you saw the solar eclipse either like 2 years ago or the one back in 2017? Yes, yeah. So when
Wait,
you look at a
last
solar
year?
eclipse, you look at it through your special glasses and you can see white light. That's what you're seeing as you're watching the sun get covered up. It's white light that's coming through those special eclipse glasses. But on SLOOH, when you go to the solar telescope, you look at it in what's called H alpha light. And H alpha light allows you to, yeah, the one in 2023. H alpha light allows you to see what is happening on the surface of the sun. Does anybody know how long the solar cycle is? Okay, so the solar cycle, 15 years is a good guess. It's 11 years. Yes, exactly. So solar cycle is 11 years. We're kind of coming off of the peak of the solar cycle. And at the peak of the solar cycle is where there's the most activity on the surface of the sun. And that activity shows up in these little prominences, flares. They're called coronal mass ejections, or another type that can leave. It's like magnetic activity that causes things to leave the surface of the sun or just more activity on the surface of the sun, all driven by that magnetic surface. Um, it's possible to capture water, like we've known about the existence of the 11-year solar cycle for a very long time. And a lot of it is because people have been drawing the spots they can see on the sun and recording that for a long time. One of the first people who has really done it for a very, very long time, or who did it for a very, very long time, was named Hisako Koyama. And she drew the spots by hand over time, thousands of sketches. And her record was actually used to help figure out and really verify the 11-year solar cycle. You can do that yourself on SLOOH because it is every day you can go through and even see it change over the course of a week. You can even see it change over the course of a day. So that is the first of the objects on SLOOH. How many of you have already taken a image through the Canary Island telescope, solar telescope?
Can't really, haven't really
Sorry?
figured out how to do it.
You haven't figured out how to do it? Oh, we can show you later. So when the solar telescope is online, you would go to that page under
And
telescopes.
besides, I already have 5 missions planned.
Well, you don't, it actually, bonus doesn't count against your missions because you're just taking a snap and you can take as many snaps as you want. A prominence, Mandy, is when it's like well, I can show you one on this map. It's the little black line, that's the solar prominence. It's where the surface is a little bit different because of the magnetic activity that's happening there. Um, awesome. These are great questions. So we've all seen the sun. You can see it on SLOOH. Our next object is one that we've also all seen, which is the moon. Does anybody know what phase of the lunar cycle we're in right now?
Waning gibbous.
Before
Yes.
last quarter.
Yeah, so we had our full moon toward the end of June, and we're now right? Moving to the waning gibbous before the last quarter. So the moon is one of the most commonly imaged objects in on SLOOH. In general, you can look up at it and see it most places, regardless of light pollution. So it's a really common night sky object to look at. And the cool thing about looking up at the moon is that I think it's fun to think about the fact that people have been looking up at the moon for generations. One of the most famous people who looked up at the moon and who wrote about it was Hypatia of Alexandria. She was one of the first women that we know of who actually taught astronomy and mathematics, and she used instruments called astrolabes to map the motion of what was happening in the night sky. And there's a crater on the moon named after her. And I secretly am hoping that one of the Artemis missions will go visit that crater because I think it'd be very cool if the first woman on the moon walked by the Hypatia crater. How many of you have imaged the moon on SLOOH? Nice. Yeah, it's a great one to schedule missions to. And the clarity is awesome. And you're going to get access to a new lunar telescope coming soon to SLOOH, probably later this summer. There'll be one that is dedicated explicitly to the moon all the time.
Like Chile 3 is for like moon for like the lunar telescope, but then it's for like special events only.
The Chile 3 telescope?
Yeah.
Chile 3 is for special events only. Yeah, this
Yeah.
this lunar scope is going to be actually over in the Canary Islands. So it'll be another Canary Islands telescope. Yeah, I'm so glad you think SLOOH is fun. Yeah, Canary 5 is offline right now. I think it's actually Grace is the person to say why, but I'm pretty sure it's because it overheated a little bit. It's hot everywhere right now. Okay, our next object that we're going to talk about is Vega. How many of you have heard of the star Vega? It's a super common one. Have you ever watched the movie Contact or read the book Contact?
I mean, I've heard of it.
Yeah, so they also talk about this star in that, which is a fantastic movie and fantastic book by Carl Sagan. So if you like science fiction, but
Apparently it involves like going to Vega for something.
I'm not going to spoil the plot. You got to read it or watch it. But it's a great book and a great movie. So Vega is one of the brightest stars in our sky. It's a blue-white star that's very hot, that a lot of sailors and stargazers have used to navigate by for a long time. Before we had GPS, all navigation was done with the stars when you were out on the ocean. And people use these tools called astrolabes to be able to map the distances between stars in the sky and use that to orient themselves. One of the women who did that, her name is Miriam, and she was one of the first and finest astrolabe makers that we know of. And her ability to make those tools help people be able to move across the oceans and be able to navigate with ease. And there's actually an asteroid named after her now, which, if you get really deep into SLOOH, you can actually image asteroids as well. It's a really amazing story to think about how people would set out across an ocean with no GPS, no any way of no maps, know of who also has gone there, and be able to just use their knowledge of the night sky, use the tools that help them measure distances between the horizon and the stars and stars themselves and where the stars are in the sky, and be able to get where they're going and then more impressively come back. So I love thinking about that and learning about that. Our next object was actually, Grace and I didn't plan this, I promise, but it's the Crab Nebula, which is one of my favorite objects, partially because it's a beautiful object, but also because of the story behind it. As was mentioned earlier, it is a supernova remnant, and it also has a pulsar in the middle of it. Jocelyn Bell Burnell was the one who discovered how pulsars work. And her data helped us to understand this new type of object that was able to provide a glimpse into what happens to stellar remnants and into why these markers of noise in the night sky have such consistent timing. She was a female in astronomy well before that was super common, and her data was something that everybody kind of wanted to dismiss But she persisted, and that study of pulsars is a critical part of astrophysics today. Our next object is the Horsehead Nebula. Um, what is a pulsar? I'll go back to that later. The Horsehead Nebula is another beautiful object that you can image on SLOOH. It looks just like a horse, hence the name. Astronomers are not very creative at naming things. My personal favorite example of that are the Very Large Telescope, the Extremely Large Telescope, and the Very Large Array. Just not a lot of creativity in those names, but you know exactly what they are. Um, so this particular nebula was one that was noticed by one of the Harvard computers, as they were called, the women who analyzed glass photographic plates and looked for differences in the stars, looked for any way that they could catalog the stars on these plates. She found the Horsehead Nebula, and she um, later got credit, but not till much later. And is an example of somebody whose persistence and diligence and dedication to detail helped us discover new objects and new beautiful parts of the night sky. So definitely recommend adding this to your list of things to look at on SLOOH. Next up is the Sculptor Galaxy, which was discovered by Caroline Herschel. She's the one who I would name my dog after, not the more commonly known Herschel. Caroline Herschel was also a brilliant astronomer in her own right, and she was one of the first ever women paid for scientific work in Great Britain. She discovered the Sculptor Galaxy along with a bunch of other galaxies and comets. There's a whole quest on SLOOH that is all about Caroline Herschel's discoveries, and you get to collect a bunch of them and add them to a poster and learn about what each of the things that she discovered are. So definitely would recommend looking up that quest if you're interested in learning more about Caroline Herschel. Yes, wow is exactly the right response. Awesome, and thank you for answering the question about the pulsar. I'm happy to go back and chat more about that. The next one is Henrietta Swan Leavitt, who helps study a special kind of star that brightens and dims like a slow heartbeat, which we call Cepheid variable stars. This huge cloud has packed with these stars, and it has some of them in it. When you're measuring distances in astronomy, we use a bunch of different markers on what we call the like a ladder of distances out. So when we're inside the solar system, we can measure a little bit more easily because we can use geometry within the solar system and figure out how far away things are. But when you get further out, you have to use different scales to measure different distances. And what she discovered is this relationship between the pulsar and, or sorry, the Cepheid variable star and how bright it was with how far it was. So there's this relationship that's the period and the period also. So the period luminosity scale and the luminosity is related to distance. So you can back out how far something is from the period of it. And she was an incredible scientist to figure out this out, put it all together. And it's an incredible, important part of how we measure distances to other parts of the universe to this day. Her work was done in the early 1900s, and we still use Cepheid variable stars now. This is the last one I'm going to talk about. It is my personal favorite. Vera Rubin is an amazing woman. Does anybody know what Vera Rubin is famous for? I mean, it's a little bit on there, but like, have you heard about Vera Rubin before?
Like this galaxy, like the Andromeda galaxy.
Andromeda Galaxy. What did she find in
She
it?
has pretty sure that she helped find out like dark matter by finding out that the finding out like the edges of the galaxy don't orbit at the same speed.
Has anybody heard of dark matter?
Yeah.
I've heard of dark matter, but and I've also heard of Vera Rubin, but I don't know much about it.
Well, then let's learn. So, dark matter is something that is holding the galaxies in the universe together. So, Andromeda is our closest galaxy. It's about 1 trillion stars. It's about 2.5 million light years away. In the late 1960s, Vera Rubin was measuring how fast the stars were moving around the center of the galaxy. And what we would have expected is that it would follow a Keplerian, so Kepler's laws, it would follow a Keplerian curve, and we would know, we'd be able to predict with physics exactly how fast the stars that are far away from the center of the galaxy are moving compared to the ones in the middle. Math, physics that you all can do would be able to tell us that. But instead, what she found is that instead of the Keplerian curve that was expected, it held steady going out. And that suggested that there was more matter there than expected. And nobody's been able to figure out what that matter is that causes that continued the higher speed. And we just call it dark matter, which is again another example of astronomers being creative with naming things. So dark matter is still a mystery. I can't answer what it's made of because we don't know. It is that and dark energy are two of the longest standing mysteries in astronomy, and I don't know if they'll be solved within our lifetime. I think there's a lot to learn still. There are some really cool experiments that are being done to try and measure the existence of dark matter. There are hypotheses out there about whether it could be a certain kind of neutrino or a different particle, but nobody actually really knows. But what's really cool is that she discovered it. And it's something that would have been really easy to mark off as a fluke in the data, or oh, I did something wrong, or people to dismiss the data, but she really proved her case and showed that the stars are moving far too quickly for all the matter that she could see. And now we have this incredible mystery in astronomy that nobody has been able to solve. She also did a bunch of other really cool research in cosmology, if you're interested in diving into her history. All around, an absolutely incredible scientist. So all of these are objects that are captured. You can capture them on SLOOH. You can all go in and learn more about these different astronomers and all their amazing discoveries, the Carol Ann Herschel quest, and actually later today, these objects and more information about these astronomers will be published in a special quest that you all will also be able to do. Um, I think it's really fun to learn about the history of the people who discover these things in the night sky that we learn about. When we read it, it can feel so common sense. But in reality, there's often a huge story behind it that often involves a lot of uncertainty, as most science does. And learning about what are the steps that let people to ask the questions and then make these discoveries is one of the most fun parts of science. Yes, I see you have your hand raised.
What about the SLOOH 1000? Like, I found an item from it and I captured it, but is that like also a race or something?
No, it's not a race to capture the SLOOH 1000. There are a lot of people who try and capture all 1000 of them, but that takes a long time. But I'm so glad that you're starting to get images of them and make your collection. That's awesome.
Okay.
Um, and with that, I'm happy to answer any questions about the women who I talked about, their discoveries, or any exoplanet or astrophysics questions.
Real quick, just observation. This is Kevin Cobble again.
Yeah.
When I was in college, over half a century ago now, my advisor Guido Chifarini did a lot of the observations for Vera. He went to
That's
Cape Peak and to Chile, and
awesome.
kind of a historical thing. Back then, it was missing mass. It wasn't dark matter yet. They
Yeah.
just knew we're seeing, we should see mass, we're not seeing it, and so it was called missing mass. And then later, dark matter.
Yeah, that's a great Yeah, great historical note. Difference between a prominence and a solar flare. Oh, you're going to test my solar physics knowledge here. So solar flares are associated with when there's an ejection of particles that come toward the Earth. We see them in the solar telescope, but then they also can produce coronal mass ejections, which cause interference with satellites and things like that on Earth. Prominences are more you can imagine it like it's like a bridge that pops up on the surface of the sun when the magnetic field is reconnecting, and then it doesn't necessarily cause the coronal mass ejection. Great question.
Ma.
Any other questions?
Nope. Nope.
Okay. Well, we're so happy that you all are enjoying SLOOH and having this wonderful, wonderful program. Huge kudos to your organizers. Oh, who is my favorite astronomer? So my favorite astronomer is a woman named Netta Bakal. She was actually friends with Vera Rubin, and she is the head of the department at Princeton. She has been working in astronomy at Princeton from she was in her late 80s when I was there, and she'd been there since she was a postdoc. So she's an incredible leader in the field. Studies cosmology, which is the study of like the Big Bang and how the universe started. And I I loved learning about her work because she also was connected to the science policy side of the world too. So her husband was also an astronomer, and together they did a lot of advocacy in DC in the late 70s and early 80s to help create the what would eventually become the Hubble Space Telescope. And worked with Nancy Grace Roman, who the telescope that's launching later in this year is named after, who was the first director of astrophysics at NASA. And I think the connection of science to policy is just absolutely fascinating. Am I an astronomer? Yes, I am an astronomer. I'm an astrophysicist astronomer. You can use the names interchangeably. My PhD says astronomy, my undergrad says astrophysics, but it's really just how much math you're sticking in it that changes people's names. I'm so glad you want to be an astrophysicist. That's awesome. I hope you are. I hope you will be. You're on the right path. Well, and if any of you have any questions that you think of after, you can send them to your organizers and they'll pass them on. And we're just so glad that you're on SLOOH and enjoying this, interested in science and astrophysics. So many future astrophysicists. That's awesome. Which theory do I believe the most for how the universe will end? Um, hmm. Well, there's a bunch of different, there's the like big expansion or the big rip where it tears apart, and then there's the big collapse.
Yeah, the
I'm
big
gonna give you
crunch.
in the big crunch, yeah. So I'm gonna give you the scientist answer, which is that
Like the heat
I
death is
want to
one
wait.
of the heat
Yes.
like heat
Yeah.
death is the more like popular one.
Yep.
And assuming proton decay doesn't occur, you get really interesting stuff.
That to my cosmology friends, but they're great books to read about it.
Katie Mack's book is fantastic.
Yeah.
And has a beautiful, Emma talked about the blending of science and policy. I feel like Katie Mack does a wonderful job of blending science and philosophy almost as we consider the end of the universe.
Yeah, her book is excellent. Another one, if you're interested in cosmology side, is by Professor Joe Dunkley. Um, we can send over a reading list. There are lots of good books. Cool. Awesome. Well, thank you all so much. Enjoy the rest of your time. And I hope you enjoy the rest of the SLOOH presentations as the rest of our team pops in this week. Thank you all.
Thank you, Dr. Emma, and then Grace. Tyler, can you prepare for the next? Do we need to have a brief break time?
Yeah, we'll have a. How long of a break do you guys want to have before we go to the next activity?
It should be a 10,
Let's
10
say 10
minute break.
minutes. 10 minute, 5 minute maybe.
Guys,
we need a negative 10-minute break.
5 minutes, 5 minutes,
10 minutes.
5 minutes.
Okay, vote in the chat.
Probably
Yeah,
can.
just do a 10-minute break. That's standard.
Yeah, 10 minutes break.
Back 2:05.
All right.
Okay.
So 2:05 we will reconvene.
Okay, see everyone back at 2:05. We'll talk about a lot more stuff and we'll have a really fun activity today.
Okay.
I have no idea what you're talking about. I don't have any business. I'm retired. And Z-Field is not a real business.
Anson.
Okay, yeah, open this breakout room so we can quickly talk about the presentations.
Okay. I can't keep recording when I'm in this room.
Oh.
Yeah. But anyways, let's just keep talking.
Yeah, okay, so I have deleted a few sections from this thing, because this would take like 2 hours. I've also
Okay, everyone, that's the end of the break.
That was chaotic.
Very chaotic.
Anyways, the next thing we're doing is the Harvard Smithsonian Telescope. Let me go ahead and share my screen. So this is a sort of alternative to SLOOH, except the Harvard Smithsonian Telescope has its own image processing software. So what we're going to do now is teach you how to take an image with this telescope. So the link is in the chat right now if you guys can all open it. And then I'll lead you through the plan. Has everybody opened this page yet?
No.
Yes.
Yes.
Yeah, I'm going there. I'm going there.
This is our alternative right now in case SLOOH breaks down again.
Mine didn't.
Okay, has everybody opened this yet?
Yes.
Okay,
Yes.
so I'll start now. Oh, not yet. Either way, I'll start now. You can catch up later. If you have any questions, just ask. So the target that we're going to be imaging today, well, later will be the moon. So go ahead and click moon for this, and then click zoom view, and then click 30-second exposure time. Actually, 1 second exposure time. Actually, 0.1 second exposure time. Whatever exposure time you guys like, and then click a gray filter, and then press continue. And then you can type in your email, type in all this, and then tomorrow they'll send you the telescope. So yeah, they'll send you a image of the telescope using this.
I didn't see my age because I'm too young.
Um, you can lie about your age in order to use this.
Oh, I'm just going to do the easier, the smallest.
Okay.
Wait, so do we just wait until tomorrow and they're gonna send it?
So has everybody done these steps yet?
Almost.
Okay, I'll take that as a yes. Does anybody have any questions about how to do this? Or no?
Yeah, what's the exposure time for?
So how exposure works is how much time a object will be pointed at the moon. For example, if we go back here, go to moon.
Wait, Tyler. So exposure time is essentially how long the camera shutter will be open for, and that governs how much light is let into the actual camera.
Yeah. So
Oh,
I'll go ahead and like make an example where I do a 60-second exposure. That way we can have an example tomorrow. In case you want to, for everybody to look at.
wait,
That
so
way
is
we
it
can have
just
a
gonna be like
comparison.
super bright?
It will
It's
be
just gonna
super
be,
bright.
oh,
Here, I'll give you an example of overexposed versus unexposed image.
there's unexposed image.
Here's a good example. Yeah.
Oh, yeah, okay.
So
That's
basically,
cool.
if you have a phone or camera or like anything that can take photos, you should be able to adjust the brightness of the photo, and that's basically what this is.
Yeah.
Cool.
So now that we've done that, tomorrow we'll cover how to do image processing with this. Or what computers are you guys mostly using right now? Are you guys using a Windows computer or?
Windows Dell.
Windows, Dell. So
Microsoft Windows.
Windows.
Microsoft.
Raspberry Pi.
what?
What?
I'm using Raspberry Pi
What was
definitely.
that? Oh.
Wait, no one has a Raspberry Pi? That's crazy.
We have Raspberry Pis, we just don't use them as computers. So that's our quick telescope tutorial. Much else there. If you guys have any questions, we'll cover more about this later. So basically, this is just an alternative SLOOH in case you guys run out of your imaging times and stuff. If you run out of your SLOOH stuff. Okay, so now that we've done that, the next thing we'll do is it's on the schedule.
Are we gonna play Blicket?
We'll play Blicket eventually.
Can we?
We'll
Oh,
play
okay.
it after Hanson. We'll do it after Hanson's presentation.
Yay.
So
Come on, Hanson.
has anybody taken a photo of with SLOOH yet?
Yeah.
No,
I took a photo.
Not really.
I took a photo of Mars.
Quick question: how do you even log? Is there like some sort of login code to SLOOH? I can't really figure it out.
I took a photo of Mars.
I took at least like 10 photos.
I took one
More
photo
like 30
of Mars.
photos.
I took A.
I'm
I took A.
I've taken like 30.
Right now I've taken 2 photos of Mars and I'm doing a second mission right now. It's running.
I've already got a whole bunch of missions.
Quick question: is there some sort of login code to SLOOH?
Okay, so this is everybody's images so far. So, who wants to present their image?
I have none.
I have one.
I have a whole bunch.
Put your who's Malieth right?
That's not me.
Hers has way too many gravity points. Got it.
It like the top 3 are mine.
Top 3 are yours? Okay, so do you want to go ahead and present your
yeah,
image?
like these 3. Yeah.
Yeah. Yeah, sure. So
Like
this is
basically I was hoping for like a color image. Unfortunately, I only had grayscale ones.
good job. As you can see here, this is most likely a satellite or a Starlink satellite.
Also have a like one color image, Caldwell 33.
This is under exposed. You should have something that you could do
Yeah.
with this is like get more exposure.
I didn't really manage.
I have a question. Like, how do you put an observation? I captured an image, but I don't know how to put an observation.
So you put your observation by coming over to here and adding observation. I've taken images before. It's just that my SLOOH has been glitched out so many times that I can't do a thing.
Yeah, so this one you have to like go to something else and then go back to observations, I think, when it glitches.
Yeah. So this is also your image. I believe this is someone from SLOOH because there's no way that someone has this many gravity points here.
Yeah, bro. Who's been grinding on this?
So Gabe, also someone that has way too many gravity points.
Real quick, someone has a question.
Yeah?
You can You can unmute and ask it.
有没有回答问题啊？要吧？
Me?
Yes, you can
Oh,
answer.
oh,
You got a question?
I was just wondering, I was trying to get in onto SLOOH, but it says they have to pay money, so is there something like login code?
Oh, you have to delete all your cookies. Yeah, that
Oh,
was the same problem I had yesterday. Basically, there's a button to the left of the link, like directly left to the link. All you have to do is click on that and then clear your site data and cookies and then reload.
oh, okay, thanks.
The SLOOH telescopes are aimed way south, 72.5 degrees south of the equator. So we're
Gibbon sounds
talking about
old.
only 18 degrees from the south celestial pole at a object that's inside of the nearest companion galaxy to us. You might think, oh, that must be the Andromeda galaxy, but no, that's the nearest spiral galaxy. But there are two dwarf, irregular.
Sorry, but I had to mute you.
Interesting. He was giving us some ASMR music.
Yes, I believe that is the SLOOH talk whenever you do a mission. Right now, Australia 1 is here. Since I have a teacher's account, I can watch it live.
Yeah, like anyone could do like watching it live.
Yeah.
Wait, are there any like live SLOOH telescopes that actually move?
Well, the live ones
They
are
move really slowly.
They
someone's
what?
using them right now, so
Oh, so we can't see them.
yeah. I believe the observations are mostly glitch so far. But Arav, an actual person, do you want to share your image of Mars? Tell us about it.
Oh yeah, I also got these two images. It's just that I didn't send an observation.
Hmm. So for Mary's question on how to capture an image, I can quickly show you a tutorial. So basically, you go schedule a mission, depending on whatever telescope you want to use. Uh, let's see, Canary 3. Go over here, reserve the slot. Oh, the catalog is glitched too now. Okay.
It's by SLOOH 1000, I think so.
The catalog is glitched. When you click on choose
Yeah,
catalog, it
yeah,
says no
catalog never
options.
works. Choosing catalog
It's,
never works.
it
Yeah,
says no
catalog never
options.
works.
And
Catalog
also,
never works.
SLOOH stole my advanced mission time slot. I was trying to look for an advanced mission time slot today, and it said I already used it even though I hadn't done anything.
SLOOH has been glitchy a lot lately. I can go ahead and go ask Anna about advanced missions and how.
I did put something on hold on accident, but I'm pretty sure that doesn't mean it uses up my limit, right?
If you put something on hold after an hour, it should like delete itself, so you should get your mission back. Honestly, I'm not sure. Most of SLOOH is kind of glitchy right now. There's a lot of bugs. So the telescope works well. While we're here, we could go ahead and give a talk about catalogs and stuff. So most of you already know Herschel. So Herschel was the creator of the Herschel 500. So the Herschel 500 is a big list of stars, double stars. So yeah, the other major one that you should probably know is also Messier.
Yeah, I know Messier.
Yeah, but then the Messier has a few issues, so now they use NGC.
Messier. I think it's 100.
It's a
I think it's
hundred
101. Yeah, I think it's 100
It's
or
110.
oh,
ten.
yeah, 110.
And then so Messier has this list of 110 objects. You can view all of them in March. It's March, right? Yeah, it's March. In the thing called the Messier Marathon. So SLOOH also has this thing whenever it goes to March. Do you have a question, AQ or Felix?
Yeah, and please don't call me that. I'm still trying to log into Subaru. Oh, I can't really figure out how to get rid of the cookies. And yeah, it just says like buy a seat for like 4.99 a month. Yeah, I tried logging in that stuff. Yeah, it says I have to pay 4.99 a month for one seat thing.
Okay, I'll go ask Anna about it right now.
No, I mean, oh, Eddie person. I mean by him calling me Felix. Yeah, that's my initials, by the way.
Okay.
Wait, how do I see the SLOOH objects that I collected?
You go to your dashboard and then you scroll all the way to the bottom, and then it'll show you all your photos which you've collected.
Okay, so that's our quick talk about SLOOH in general and how to do stuff with it. So next up on the list is Hansen and asteroid mining. And then
Yo,
after your
Okay,
Blicket.
real
yo,
quick, number
Tyler.
one catalog. uh, Tyler, the other
Yo,
one
is
mentioned was the Caldwell.
The
Yo,
Caldwell?
Tyler, you didn't answer my question about the
I swear this is glitch. SLOOH is so glitchy.
What question did I
Eastern
not
time.
answer?
the thing about the paying thing. Like, how do I like not pay, like, and still be able to use SLOOH?
Oh,
Is
you
everyone paying?
you have to create an account.
Yeah, but it says it's like creating an account costs money, kind of.
Mm,
Yeah,
I think you have to go to the login thing. I think you
yeah,
might have to go to the
yeah.
login.
I did the entire login thing. Um,
I think you should log in with Google and then I think I'll give you an account.
I mean, I
Okay,
did log
It's
in with
it's
we can
obviously a
Google.
bit buggy right now, so
I did log in with Google.
we can
Yeah,
talk
it didn't
about
work.
this later. I've already emailed Anna. She should be going out to help and ask them about that problem. So, anyways, the Caldwell catalog is another amateur astronomer catalog about another famous astronomer, Patrick Moore, as a complement to the Messier catalog. It's basically another catalog, not much else to it. The other one that we can talk about is the NGC, which is the new general catalog. This is a big catalog with a bunch of objects. Most objects in the sky are in this catalog, like most big famous nebula.
Yeah, all the Messier, all the Caldwell have NGC catalog numbers. Yeah.
Mm.
Yeah, the Caldwell is a complement to the Messier, and it was Patrick Moore is a famous amateur astronomer who thought that there was a lot of objects that you can see that are bright that aren't in the Messier catalog, and so he created his own of 110 objects once again, and there's a lot in the southern hemisphere. So there's some of those objects in the Caldwell catalog you can't see from here. You can only see them from the southern. But it's you'll see, especially in the SLOOH, when you go through like the SLOOH 1000 or whatever, a lot of them have Caldwell numbers instead of Messier or NGC.
Okay, so that's basically our short thing about catalogs. Now we'll go back to Hansen with his presentation about asteroid mining.
Okay, let's get this thing pulled up. So, who here has like heard of anything or like read anything about asteroid mining? Just raise your hand. Just want to get like a feel of the room.
Asteroid mining?
Yep.
I've
What?
heard I've heard of it, but like I don't know anything.
Oh, I mean, from what I've heard, basically you launch a big ass rocket, you land it on an asteroid, and then bunch of guys in spacesuits somehow
Yeah,
drill.
that's not very feasible, like just landing a rocket and collecting it, but
Well, I
at
mean,
least
based
at
I
least
Okay,
it's
have
okay,
more
okay.
no
feasible
So,
clue
than
about
taking the asteroid
anything.
in a net and mining it.
I have
yeah,
no
so
clue about anything about this.
hopefully this presentation will clarify anything that you want to learn about asteroid mining. So let's get started. So here's what we're just gonna be talking about, some stuff. So before we can understand how like extracting stuff from an asteroid works, we have to first understand what an asteroid is. So can anyone raise their hand? Just tell me what they think an asteroid is.
Big piece of rock.
Yeah, pretty much. It's just a big
Big
piece of
yeah,
rock.
Big piece of
big
rock
boulder.
rock
floating
with
in
stuff
space.
inside.
A
Yeah,
Like
big
but
boulder.
piece of rock floating in space.
yeah, but it's also not just rock. What else can it be?
It can be
Iron.
ice.
Ice,
Platinum,
dust,
Ice. It can be
gas.
ice.
gold.
Yep,
Ice.
ice. Yeah, ice, metal, rock. That's pretty much what they're mostly made up of. It's good. So, but and obviously, like since space rocks, there are different classifications for them. So an asteroid is just a large rocky or metallic body, so specifically not icy, orbiting the sun in space. A meteoroid is a lot smaller, like stuff that's probably like the size, like you fit in your hand. A meteor is a meteoroid that burns up in the Earth's atmosphere, and a meteorite is a fragment of it that survives the actual atmospheric entry and lands on Earth. Something I did forget to include is comets, which are mostly made out of ice and gas. And like when comets come around, you usually hear about them because they're pretty cool. So here's where most of them are found. So a large proportion of them are found in our main asteroid belt, which is located between Mars and Jupiter. So it's essentially just a remnant of one of what happened after the solar system formed. It's essentially just a bunch of like waste after the planets formed, pretty much. Some people also think it could be because like another planet like was there and it fragmented for some reason. So that's something else. There's also near Earth asteroids, which are asteroids because of their interactions with planets like Jupiter or like or probably Mars or something. Their trajectories bring them close to Earth. So those are like really nice to look at because first have to note if like they're not going to hit us or not. We also have to find out. They can also be really good for mining because they're pretty much come to us. Now we don't have to go to the asteroid itself. And then there's another group of asteroids called the Trojans. So these are asteroids trapped in the Lagrange points of planets. The Trojans specifically are Jupiter's. They orbit on Jupiter. So they share Jupiter's orbit, and there are some missions currently that are planned to go there and investigate them. Yeah, Arif?
I watched a video on YouTube and then they said like they track asteroids from like a large building which has like a telescope on top,
Mhm.
and then they can track like four pictures and then they can see if there's anything moving towards Earth.
Yep, it's good. So now let's ask why we actually need to mine these asteroids. So give me a second. So obviously, since we live on a planet, we have a finite deposit of elements. Some of them like just like coal or it's not even coal, like just like iron or like nickel are like really common. So there's that. And then, but then there's also elements like platinum or osmium that are a lot harder to find. And in addition to that, like mining on Earth can destroy a bunch of biomes, cause a bunch of habitat loss, and it's also kind of like bad energy. It's not energy efficient. Then in space, just like some asteroids can hold more, more like iron, cobalt, even like rare stuff like gold and platinum. Like, so it can hold more of that stuff than humans have extracted since humans have begun extracting stuff, like with barely any harm to the Earth's biosphere. So, and then we can also use the materials to build stuff in space. Then some people might be asking, why don't you just Why don't you just, launch stuff from Earth? So, thing is, because of the menace that we call the rocket equation, you're going to need fuel to bring up a bunch of payload. But if you add fuel to, lift heavier payloads, you also need more fuel to lift the fuel, and that keeps on just adding up until pretty much 95% of the rocket is just fuel. So, which is not good. So if you do it in space, you don't have to overcome the Earth's gravity because you're already out there. And you can do some small burns to get the cargo where you want it to go instead of having to launch from Earth and make it super wasteful. So yeah, and then now what do we actually want to take out of these asteroids? So obviously number one is water. So water ice is pretty much like instrumental for everything. You can use it for to just straight up drink it. You can use it to generate oxygen through electrolysis. And you can also create hydrogen rocket fuel also through electrolysis. And then there's also structural metals, so stuff like iron, nickel, cobalt. You can use that stuff to make like spaceships, like make space stations and stuff without having to launch it from Earth. And then there's also really high value, really rare metals like platinum, indium, palladium, osmium, which are essential for stuff on Earth. And they're also used in chemical reactions as catalysts. For example, platinum mesh is used to catalyze reactions, to catalyze turning nitrogen into ammonia. So, yeah, and
Yeah,
this
there's
is not
also like
needed.
helium-3. You
Mhm.
can use that for fusion, and I think a lot of times the ice is irradiated by the sun.
Yeah. So yeah, there's also helium-3. So this is not just asteroid. This is you can also if you want to
You
mine
can
stuff
just
like, for
mine
example,
helium-3 from the moon,
yeah.
though.
So also just quick safety note: do not eat helium-3. It's not healthy. So and
Don't
then now
drink
we have
deuterium water either.
you can drink deuterium water. I'm not saying you should, but you can.
Yeah.
So now we have the asteroid
But
types.
then
So here's some
tritium
types.
water, no thank you.
Yeah, tritium is highly radioactive, so do not eat it. All right, so here's some asteroid types. So we have C-type, which is carbonaceous. This is the most common type of asteroid. These are made of organic compounds and some hydrated types of rocks. So this is best for, harvesting carbon compounds in water. And then you have S-type. I'm not gonna say that. So they're like stony bodies which contain like some metallic stuff like iron or like magnesium, nickel, and like actual grains of metal. So this is best for, building stuff. So then you have M-type, which are metallic asteroids. So these are really high density, chunks of metal, pretty much, and they contain a lot of metal. And then you have the D-type, which are really rare, and they have high concentration of like volatiles, which are chemicals that have a low boiling point, and organic, which is carbon-based matter. So that's also pretty cool. So just quick organization of all these. And then now we have some proposed mining techniques. So some of those techniques you guys talked about are on here. So number one is boiling water with off of asteroids with sunlight. So C-type asteroids are the ones that have a higher water content. So you can literally just use giant mirrors to heat up the surface and then, like cause the water to boil off. And it can also cause the thermal stress causes stuff to expand, which means it can cause a bunch of stress to appear on the surface of the asteroid. You can use it to break it apart, which is also pretty cool. And then you can use a giant space vacuum cleaner to just suck it up, and then you have a bunch of stuff. And then there's also two others that are pretty cool. So there's swarms of robots, which will fly over to asteroids and then start excavating stuff. And it is good over just one big machine because you have 100 tiny machines. If one breaks, you'll have 99 machines left. But if you have one giant machine, nothing breaks, then you have zero machines left. You can't do anything with. And this is also extremely scalable. Then you have the bag and process type, which is kind of fun. These are for asteroids that are more like rubble piles. And essentially, instead of just leaving it there and like potentially losing material, you will take like a giant plastic bag or something, and literally just eat the entire asteroid, and then you'll completely confine it. So essentially, what would happen is that since you confine the thing, you won't lose much material, and everything can be done internally. So it's pretty cool. And this one I forgot to delete, my bad. And then we have some hostile space physics. So space is not a safe place. It is not a hospitable place, and it's definitely not definitely not a nice place to do stuff in. So there's obviously the microgravity. So asteroids pretty much have no surface gravity because they're pretty small. And mining tools, like you can't land on an asteroid pretty much. you have to rendezvous with it because asteroids barely have any surface gravity, as I said. So, and then there's also cosmic radiation, where solar flares, cosmic rays, all that stuff will degrade computer chips, make your solar panel die, and also not be good for people. And then asteroid dust, since there's no atmosphere or water to smooth it down, asteroid dust is very, very jagged. Like it looks like a kidney stone pretty much. It's extremely, extremely sharp. It can damage a bunch of stuff like seals. It will like absolutely tear stuff to shreds and also cause static discharges because there's no water. So yeah. And then we can also ask a question whether it'd be better to have people or robots to go. Just read this. This I won't go into too much detail to because it's not super there. And then we have space engineering. So this is the techniques that we can use to actually do this asteroid mining. So you might remember this from yesterday, but I talked about ion engines. So ion engines are very good for like or doing very long trips because they have extremely high efficiency because of their tiny amount of thrust. So we have that. And then there's also some anchoring systems that you can use that we might be looking into, like, microspines, literally just shooting a giant spear at the thing and then like reeling it in, or like screws to like lock like the extractor to the actual asteroid. So that's some stuff you can look at. And then AI can also be used to help find landing spots because a lot of asteroids are outside of communication range with Earth because of the light speed delay. So they could be up to minutes of delay or even hours of delay before you get a response. So you have to have stuff on board that will be able to control it. And then we have economics. So I see you guys talking in the chat about how, like, if you were to bring like an asteroid's worth of metal to Earth, you would absolutely crash the economy. And I'm just gonna say that right now, that is pretty true. Like,
Because basically what happened to Germany right before World War II.
Yeah,
yeah,
it's
pretty much.
inflation. It's too much
You
inflation.
just have
Yeah,
hyperinflation, but worse
yeah.
hyperinflation.
Yeah,
What's
then
happening
like
to
So
Zimbabwe
then the
right now?
whole economy will crash because if everything is the same price, then there will be no more left, and then it'll be scarce.
Yeah, so
yeah,
basically the cost shoot up whereas your income does not shoot up. Therefore you need like a whole wheelbarrow of cash to buy
Supply and
like a cup
demand.
of coffee.
Supply and
yeah.
demand.
Okay, I'm gonna go on. So something that is good is that launch costs, like so per kilogram, launch cost has gone down quite a bit because of reusable rockets, SpaceX. But the thing is, if you bring in a bunch of metal, as I said, it would crash the market price of whatever you brought in, pretty much. So it is not really good. The only reason the markets haven't crashed now is because it's still in space. So for now. And then there's environmental impacts. Even though we're not mining on Earth, there's still going to be a lot of impacts. So, as I said, earthbound mining it creates a bunch of greenhouse gases, habitat loss, and destruction of biomes, and also looks kind of ugly. The space resource mining is good because there's not really much disruption to living ecosystems, but rocket launches do produce a lot of pollution because of their exhaust. So, like that is an issue, but it
Like
can
the
be managed.
exhaust produces hydrochloric acid.
Yeah, it can and must be managed responsibly, obviously. So obviously hydrochloric acid is not a good thing to eat. So yeah. And then we also have space law. So how do you tell like if you like own this rock in space? So there's stuff like the Outer Space Treaty, which says that no nation can claim like that this like planet is ours, but they say celestial body. But then there are modern laws that allow companies, not the actual country, to own the like materials and stuff. And then there's also space cooperation that is going on to help, like if like space mining becomes like a big thing, there's obviously going to be people fighting over it. So there's going to be like cooperation between this, hopefully. And then we also have some space mining missions. They're not there to make money. They're just as check stuff. So we have some missions like Hayabusa 2, OSIRIS-REx, the Psyche probe, which are all probes they're happening that have actually I think happened, where where they went to asteroids to touch them, bring samples back, and then people will then look through them. And then there's also I didn't add this on there because this is technically not like mining, but there's a probe. I forgot exactly what it was called, but it went up to a comet and took a sample of the comet dust, that was trailing behind it and brought it back. So that is also something that we've done too. So yeah, and that's it. So if you guys got any questions, just hit me up. And yeah, we'll be doing like a book or a Kahoot or something. I think Tyler found one.
Can we do monsters, bro?
Potentially.
Yeah.
We're doing a bucket.
Yeah, okay, we'll do a bucket then.
Oh,
Tyler,
can we not do
Tyler,
Monster
can you
Ball?
send me a
Can we do
list?
can you do Crypto Hack? That one's because Monster Ball gets kind of boring the more you
Let's just do
grind.
Monster Brawl.
Guys, can't we do
Monsters
Kahoot?
Brawl is good.
Let's do Kahoot, bro.
Monster Brawl.
Something that's not Monster
Monster
Ball.
Brawl.
Sure, Deceptive Dinos is
Bro.
also fine.
Yeah,
Deceptive
Monster
dinos,
Brawl.
deceptive dinos, deceptive
Hanson,
dinos.
Don't
That's a
do
good idea.
deceptive dinos.
What
Okay,
about
fine, not
clowns?
deceptive
Hanson.
Do Monsters Brawl.
Don't do
Monster
Monster
Brawl.
Ball. It's actually doo-doo.
No monster
Okay.
brawl.
Hanson, you have a
No
question in the
monster
chat.
brawl.
Yeah, don't do it.
Monster Brawl.
Oh yes.
Don't do
What is the
Monster
So I
difference
missed
Brawl.
between
that.
comets and
So a
asteroids?
comet, the comets are mainly made out of up of water, ice, and volatile gases, and asteroids are more like rocky and metallic. So hope that helps. Okay, Tyler, I'm gonna pick a random one. Give me a real control.
Monster Ball. Just don't do Monster Ball. Anything but Monster Ball. And classic.
Please don't do Monster Brawl.
Yeah, don't do it.
Either
Do
Gold Quest.
Fishing
Yeah.
Frenzy.
Either
That's a good
Gold
one.
Quest. Yeah, do Fishing Frenzy.
Yeah,
Okay, fishing frenzy, bet.
Fishing Frenzy is rigged.
Fishing Frenzy.
Can you mute everyone?
That's the best one.
Fishing Frenzy is rigged.
Don't do it. No.
145016.
Come on.
145. 145.
Wait for me. Wait for me. I'm my AirPods ran out of battery. Please wait.
Hanson, can we have like a separate Kahoot?
So if I had to make a Kahoot, I'd have to like spend a lot of time. So
Alright, I'll see you when it ends.
yeah. Can you not just find a different computer and play
No.
Kahoot? Oh.
What? But I don't know like the questions or anything.
You can play this again.
wait, just to say, I cannot stay on the meeting for that long today because I have other stuff I need to do.
Okay.
Mute.
Wait, Tyler, if you won, I could just create a Google Slides and send it to y'all, and y'all could just look through it.
Yeah, sure.
Cause I'm gonna be very busy, so I'm just gonna probably just create something on my own and probably just share it to y'all, and y'all could just review on your own.
Yeah, sure. Okay, is everybody in? Actually, no, that's 16 people. We have 32 people here. Is everybody in? Or okay.
Are we starting?
We aren't starting yet.
Oh, okay. Sorry. I thought you said go something like that. Sorry. Whoops.
Get in.
We're waiting for more people to join. There's some people that aren't in
I
yet.
can't get in. Can you wait for me?
There's a link that I sent out. Just click on the link.
Okay, wait, just go
Very
on
sorry.
just go on the web browser, go in your search engine and just search up look at .join and then you can just use the code.
I'm very sorry, Eddie, that you cannot play Kahoot. No, play Bucket. I'll see if I can make a Kahoot that you guys can play.
Kahoot is bad.
How about Gimkit?
No, I don't want to get okay.
I
That's
could do gym kit, but
that's
we
the
need a
worst
paid
one. That's the
account, and I
worst
don't
one.
have that much money.
Ginkgo's actually really fun though.
I don't think you need money to make
Yeah,
it.
that's why it's the worst.
Yeah, you don't.
We're gonna start this booklet or something.
Oh
Or
wait, never mind. You do need money for over 5 people.
Okay, we get it, Eddie.
We have more than 5 people, so yeah.
Tyler, are we gonna start the
Bro, you
booklet?
have more than
Yeah, we're
20
gonna start
people
the
to
booklet
start.
now. Late joining should be allowed. Let's go. Uh, okay.
Alright, guys, who wants to bet on who's gonna win?
Guys, stop targeting Eddie. He has his own things. It's fine. We'll just play Kahoot
Already?
later.
Hello? Is anyone here? Hello?
Mute,
Kicked out.
mute right now.
I got kicked out.
Hey, Tyler.
Yeah.
Is something? Oh, you still working on something?
We're doing a Blicket right now.
Oh, okay, yeah. Okay.
I got first place.
This
Congratulations
was so rigged.
Wow.
to
This is so rigged.
KOCM.
I mean,
Oh, I got Rainbow Narwhal 2 times in a row.
I,
And
I
still got
I got a megalodon
I
This
got
is
5 times.
really rigged.
6 megalodons in a row.
I got 5 megalodons in a row,
That
but
is like the most average thing I've
I
ever
got
heard.
sixth place in 93%.
I
honestly,
got
bro,
2 alien ships.
yeah,
bro,
I can
That's
I
really
got
easy to get.
99%.
caught a couple
And
English
then
weapon narwhal things.
I got
That's
88%.
also really easy to get.
Uh,
Well, good job, everyone.
That
honestly,
was fun.
I don't know why he won. I don't know how, honestly, but yeah.
It's called skill.
No, it's called luck.
Bam!
Same
Pure
thing,
This
luck.
is
same
all
thing,
luck.
same thing, same thing,
I just
same
put it
thing.
up.
It's the
I
same
grabbed a
thing.
new
I
megalodon.
think it's luck. It's just pure luck.
Yeah, and it's not pure luck, but
It
it's
is pure luck.
no,
It's
it's
pure
not.
luck. It's
No.
pure luck.
It
Like
depends on how
But it
fast
kind
you
of
can
you
matters
answer
what
the
can't control
upgrades
what
you
you
question.
get.
get. You
Like
The
can't control
upgrades.
what you get.
13Ks and
You
sometimes.
kind of can control what you get.
You can control how fast you get the things that you'll get.
You can get upgrades and it matters.
You don't control what the
Okay.
Upgrades
Uh,
don't matter because the upgrades are also by chance.
Yeah,
They're
upgrades
not.
are also by chance too.
okay, everyone. Now that it's quiet, we'll go ahead and go to our next phase, which is introducing our activity for the rest of the time. So, first of all, I'll go ahead and introduce the activity. After, I'll give you a short Tinkercad tutorial. That way, you guys can know how you can do this. And then after, you'll do this activity. So, I'll go ahead and share my screen again. So, what you guys will be doing is that you guys gonna make a pitch in 60 minutes after I do a thing. After I give the Tinkercad tutorial. So here's how it's gonna work. So uh the asteroid that you guys are going to be going to is 16 Psych. So this asteroid is estimated value is 1,700 quadrillion dollars, more money than you'll ever make in your lifetime. So, and the person that wins this competition gets to choose the next look at.
What are we doing?
Wow,
We're
so much trust.
Wait, how? Wait.
so if there's no questions, I'll keep going on.
I have a question.
What's your question?
What are you doing? What do you mean by whoever won gets to choose the next one?
Well, you guys will be split up into teams, depending on how many people there are in this meeting right now. So 31. So you'll be split into teams of five, and then each person will have a time of 6 minutes to present. And this is all based on the information you learned before with Hanson's from the solar presentation.
We're making our own presentation.
Yes, you guys will split up into teams. You didn't expect this to be all yap from us old people this whole time, right?
I have a question.
Yes.
What do you mean by design something? Like, do you like make a plan?
Well, you're going to design a rocket in Tinkercad, or if you know any of these softwares, you can use
So
this
we're
too.
designing a rocket
What
to
about Onshape?
16 Psych.
You can use Onshape if you want. So part of your team is going to design the rocket in Tinkercad or any of these other softwares if you know how to use them, or any modeling software that you know. If you There's also going to be a pitch. This is also really important. So basically what you guys are going to do is that you guys are going to make a Google Slides presentation or Canva, or you can make a website depending on whatever you want. And then after, here is how you can locate Solarium. And then you can estimate most of this stuff because I don't expect you to actually launch a rocket. And since you only have 60 minutes to actually work on this. Well, more. We'll give you 90 minutes.
16?
I don't have any of the apps. I don't have any of the apps, to
You
be
can
honest.
use
Wait, what?
Tinkercad in your browser.
I don't have any apps.
You don't need as them as apps. So the first rocket you can use, or if you want to use a different type of rocket, you can. You can use traditional chemical rockets. It's the type of rocket that we use the most now. So the other thing is solar ion engines. This is more of a theoretical engine, but you can use it.
Good question.
Other thing that you can use is
Thank
a
you.
nuclear thermal engine. This has been done for, but it's not really feasible with our current technology right now. So here's some presentation requirements you can do. I'll post this presentation in the chat for you guys to all see. That way you guys can know the requirements. And then here's the estimate timeline for 90 minutes after I do the Tinkercad stuff. Here's a bunch of stuff about rockets. Here's some cost comparisons and stuff. This is just all inspiration that you guys can take. So here's a basic rubric that me, Hanson, and all the other leaders will be grading on. And then we'll start now. So does everybody know how to use Tinkercad or no?
No.
No.
I sort of do.
Okay, so
I know how to use it well.
I'll give you a quick Tinkercad tutorial. So whenever you get to Tinkercad, since this is free, you can make your own personal account, sign in with Google. And then, for example, I have a lot of emails. I'll use this one. And then it'll just make you an account. So you can fill this all in. Uh, this is not my birthday, so you guys can actually this is my birthday. Oh. So yeah. Anyways, once you get into Tinkercad, what you guys will be doing is you'll create a 3D design. So over here you have things that you can pick for basic shapes. So what this will do is it will place a block here. You can move this around using left click. Actually right click with your mouse. And then some other things you can do is this will bring any block down. So for example, I've put this up here. If I do this, this will bring it down. If I wanted to make a hole or something, I could push this here, push this down. And then the most important part whenever you use this tool is that you have to group it. So now there's a hole in there. Does anybody have any questions so far?
I have a question.
Yeah?
What are we supposed to make?
You're supposed to design a rocket.
Oh, okay. Thanks.
So here's another shape. There's this tool which is really cool. So you can draw lines to design something. So if you want to make your own shape, this is how you could design it.
Can you teach me how to sign in again?
So if you guys are all using Google, all you have to do is just click sign in with Google. I'll do it again. AQ or Felix, what's your question?
I forgot my question. Bye.
Ara, what's your question?
My question is that like is there like a thing where like in the drawing thing can you like design a
Wait,
shape?
what?
Like, can you do like, or does it have to be straight lines? Or can it be like, can you design a shape in
If you want to do curved
in
lines,
the
I
sketching
believe
thing?
you have to do this. This is a tool
Oh,
for curved
Oh,
lines.
is that loft?
okay.
Yeah, this is how you do curved lines.
Oh my god, it's loft.
That's the tool you use.
Okay.
Wait, so basically Tinkercad is easier because you can just straight up draw the rocket.
Yeah, basically that's what this is. It's the
That is
easiest
Teacher,
so
software
cheap.
for
That
this.
is so cheap.
teacher,
That
teacher.
Yes,
Can you share my screen because there's somewhere that I don't know how to sign up.
you can just press sign in over here. Uh, what's your problem right now?
So it said get approved now.
Approved? Do you have a student account or do your parents have access to your account? Maybe that
Uh,
you have parental controls. Anyway, Naveen, what's your question?
This is a team thing, right?
Yeah, this is a team thing. Hanson should be splitting you up into teams right now.
Anson, give me an unrigged team.
Okay, so that's how this will work. This is one of our only activities for with teams. Everything else will be more fun later. This is just something for team building in general, and just to apply all the knowledge that you've learned so far. So, Hanson, go ahead and split them up into breakout
All
rooms.
right, so I'm about to open up the breakout rooms. So these have been picked using pure RNG.
No.
For any of the co-hosts, if you're a co-host, don't join the room. Okay, and then for us co-hosts, we will pick a room and then go into it and watch them. Okay.
Okay.
All right.
So go ahead and join your rooms.
Don't you can pick a room.
Yeah, but Wendy, Wesley, join your rooms. Here, yeah, join your rooms. Okay.
where do I join my rooms?
It should just say join breakout room.
Just that I can't sign in.
Okay, it's fine.
The only way is to join class.
Here, I think you have a student's account. Here, did you search up Tinkercad like this? So,
Oh, I did Tinkercad, not .com.
yeah,
I
you
forgot to do .com.
so what you do is that you press sign up or log in, and then you press create a personal account, not press to just join us.
.com.
Yeah, press create a personal account.
Wait, what?
Press create a personal account.
Wait, this is just loading.
Okay. Might have bad Wi-Fi. Anyways, your teammates should also be able to
Uh,
help you too.
what?
Your teammates should also be able to help you too.
Okay.
Okay.
Start Tinkercad.
Yes.
Let me see. Start tinkering. It just want to get approved now.
Okay. Hanson, can you help her? I'm gonna go check out this room over here. Actually, Hanson's move. Okay, so did you were you able to create account, Sibin?
Yeah. Well, I got get teachers' approval or get parents' approval.
Oh, your parents probably have restrictions on your account.
Oh, but my parents are sleeping.
Oh, have someone else design the thing then. Here, go ahead and join your
Okay.
room. Someone else might be already designing.
Where do I join a room? Just
Here, cl on the bottom, you should be able to just go ahead and join breakout room.
breakout room?
Yes.
Um, no, there
No?
isn't.
Here, I'll move you then. Here. Can you do it now? Can you join now? Sibin?
Kept glitching and it kept deleting our stuff. And then and then when I was creating the website, I figured out I needed to get the image, but I couldn't get the image. So I went on Canva, created the logo on the front page, and then on the second page I
Where the
just
mic
wrote
is.
our rocket name is on a new mission. And then and then Justin left, so that means I was by myself, and then it said leave breakout room, so I couldn't do anything.
It's fine. We don't, as I said, I don't like.
Okay, so now we'll go ahead with the first group. That's Arani, Nidu, Jason, Navinth. Do you guys want to go ahead and share your screen, or do you guys want to send your presentation in the chat or email your presentation to task.ysig? Actually, you have already. I believe it's.
Might need a bit more time.
Did you share your thing with me or no?
Yeah.
Okay. I believe I'm just in the wrong account then. Um,
Wait, should we put the thing on the Canva, like
you
the
can just
design?
go ahead after, just go ahead and share your screen about the model. Or if you want to, you can. Whatever works better for you.
I think we could do the presentation first and then I could present the CAD afterwards.
Okay. Do you want to share on your side or do you want to share from my side?
Do
Oh,
it from your screen.
I can't. I don't have access or permission.
Wait,
I
what?
think I can share because I also have access to the presentation.
Okay. Go ahead and share it with me or share your own screen.
Could y'all see this?
Yeah, we can see the screen now.
All right, so we didn't have much time to do this. Um, I'm pretty sure he's just like kind of editing some stuff. Could you just give us like a minute or something, real quick?
You want us to talk or
Mm.
give you some time? who finished?
No, I'm pretty sure because I wasn't working on this presentation, so I'm just sharing the screen. So
Okay.
like like Jason, could you like talk real quick?
Okay, yeah.
Well, okay, so we didn't really finish that much. But all right. So our timeline is for us to supposedly in year one, we want to first design the spacecraft, and then in year two, we want to build and test the rocket. And then after that, from months 1 to 6, we want to try and launch and travel to the asteroid. And then our mining operations will begin from months 7 to 10. After that, we'll spend another 6 months returning to Earth, and then we'll spend another month processing the metals. So, our process of asteroid mining will be to first scan the asteroid, then land using thrusters before drilling onto the surface and crushing rock. We'll separate valuable metals and store those in the containers of the rocket before launching back to Earth. And our possible metals are platinum, gold, nickel, iron, cobalt. So this is what like
Do you think you
the
press the presentation button at the top of the screen, top right? Thank you.
uh, so our drill will be around 300 kilograms. The solar panels will be around 250 kilograms. The ore containers will be around 900 kilograms. The robotic arm will be around 450. Navigation will take around 150, and most of it, which is the fuel, will be to 20,000 kilograms. In total, that will be around like 22,000, and our ore returned is around 5,000 kg.
I'm pretty sure that's like the end of the presentation, and I'll just go ahead and share the Tinkercad real quick. Did y'all see the screen?
Yes, we
Yeah.
can.
So this is all right. Let me just. I'll just go to this view real quick. So this is we chose a nuclear thermal react engine. So this is like our like reflector area, this like yellow sphere. These would be the pumps, and this is where like the liquid nitrogen or like whatever fuel we're using would be stored, and this is like where the thrust comes out of. And that's it.
Okay, well, I guess we'll have Team Tugo, Arav, Eve, and Evan John. Well, we'll have the next team go. Who wants to go next? Or okay, then we'll have the next team go then. Sibin, William, and Alex.
No, no. Please, no. Start from the beginning.
Yeah, so just a second. So Eddie, you want to go first?
Yeah, okay. So, our mission is 16 Psych, and our company name is Space Y. As you can see, we have our beautiful AI-generated logo to the left. And this presentation was made by Alexander, me, and AFK7. Okay.
All right. Let's see. Okay, so we decided that we'd use like a hybrid-ish rocket. First, we want to use nuclear thermal, but then if we use nuclear thermal on Earth, we will have a bad day. So we use propulsion to get into Earth orbit. Then we'll use a second stage with nuclear thermal propulsion. Eddie.
All right, so this is our timeline. So starting from launch, we'll use chemical propulsion to launch. And then for escape orbit, we escape the Earth's orbit. And then for the stage separation one, we perform the first stage separation, which allows the rocket to switch to nuclear thermal. And then the second stage separation, which might be planned, is that it will allow the payload to reach 16 psych. And then once we reach 16 psych, we get all the goodies.
So basically iron nickel. So for asteroid mining, so we'll probably like set up solar panels. We'll have like ore storage. We'll have mining rovers, cargo carriers, and then the solar panels they can just be left behind so we can put the ore so we have more space to carry the ore. Similarly, the mining rovers can also be left behind.
Okay, so this is the part where we get really tough because we don't care about the cost because we know we're gonna make a lot of money, and we don't care about how much money we make because we know it's gonna be enough to crash the economy.
But if anyone asks, probably a few $billions.
And same thing for this.
We don't need to worry about it because the amount of money we will make can be used to pay for the repairs and rescue missions, and we will still have plenty left over.
Yeah.
Okay. Yeah, so guys, I'm just gonna stop sharing. Yes. Stop sharing. So yeah, don't ask why it's called powerful trug. So as you can see, like this is our rocket. I didn't really put in a lot of detail, but you can see like there's supposed to be a second stage here. There's like chemical engines, booster, and then here's where we put like the nuclear thermal engine. And then there's some detail here. This is like like an example of one of our mining machines or storage pods. And yeah, Eddie. Knock knock. Eddie.
Yeah, sorry. Switch back to the presentation.
Okay, stop sharing. Why do you want to switch back?
Because there's one more slide.
There is?
I added it 2 seconds ago. I added it 2 seconds ago.
Sure.
Yeah, it's the end slide. It's the end slide. Don't worry.
What?
Oh no.
Okay, here.
Alright, after that one.
Let me just. Oh right, yeah. The end.
Yeah, I made it on the fly. I made it while Alexander was okay. Let's go.
Okay.
How many points did we get? We got like at least 90, right? Come on. I can't be failing this, bro.
Come on.
Come on, bro. 97. I'll take 96.
Wait, Eddie, you actually got a DM?
What? I got a DM? What DM?
Did you?
No?
Okay, so that's good. The next presentation will be from Meisheng, Santiago Gonzalez, and Shrivan Sta. You guys want to present?
Yeah. What do you say?
Wait, I have one question. Can we, like we're almost ready. After I finish this slide, can we go after them?
Yeah, you can go after them. Okay. So go ahead.
Santiago, you can share the slides and I'll explain the technical guide. Because you were the one who made slides.
Great.
All right.
Okay, everyone can see it?
Insane.
Do I talk or?
Yeah, I guess you could start.
Yeah, start.
Okay. Hi everyone. This is a presentation of our company, which is Project Coriolis. This is a project that we're going to describe. This is our company is Asterisk Incorporate. This is our logo, and this is the logo. Okay, this is the mission is gonna be 6 months. The steps are short, but it's gonna explain everything. The orbits insertion around. We're gonna collect them. We're gonna go collect them and just go again to here. So this is kind of like our logo or like what do believe of this mission. So we don't see is 16 episode is see it has a rug. This is the kind of logo. This is where we're going. This is the 3D model. This is our proposal. This is how explanation of how a rocket works. A rocket works by fission. That's it. I don't know if you wanna share the 3D model.
Should I?
Okay.
Okay. Share screen design, yeah, and I'll share my screen. But can you guys keep my screen?
Yep.
This is our project. This is our engine that we are going to use for our mission to Psyche. It's a nuclear thermal engine, as you can tell by the massive warning label on the front. And it uses liquid hydrogen inside a nuclear core to heat it up and perform nuclear fission, which then causes thrust to come out. We haven't really finished our whole rocket yet, which is why we were mostly working. I was trying to put most of the detail into the engine, which I sort of did. So yeah. Anyways, that's our engine for the nuclear thermal rocket. Uh, is should I stop sharing or?
Yeah, I think so.
Um,
Okay. So has everybody presented, or is there another team?
We haven't presented.
Okay. Go ahead then.
You're muted. You're muted.
Sorry, my bad. I was muted. This was my logo. This is our logo, and then I added this page for no reason. I don't know why. And then over here, I added a timeline. And over here, I added a preparations page.
Should I do the 3D model?
Okay.
Okay, let me get our.
Let me
This
share. Let me share.
I already started sharing the rocket.
Wait. Why is text back?
Oh, I put that there. I put this text over
Okay.
here. Okay, so this is our rocket, and we kind of designed it to look like a regular rocket, except on the inside, like I like.
It uses it's gonna use its four hybrid rocket engines to get it out of orbit, and then it's gonna use its big rocket motor in the center to get it into deep space so it can get to the asteroids, and then it's gonna release its payload.
Yeah, so it'll release its mechanical arm, so then it can grab all the ores. And yeah, that's it. Okay.
Okay, so that's all the presentations. The best presentation was Project Coriolis with the company logo and stuff. That's it for today. Tomorrow we'll be doing more presentations, and then we'll also have Jeopardy again.
No.
Also,
Why more?
Anna's going in to fix the problem, and we'll also be doing image processing and how to do research tomorrow.
I have a question. Do you have any like homework or anything to do?
The really only thing is use SLOOH to take more photos. That's the really only homework we have.
Okay, but I can't get into the group on SLOOH. It's not working.
Well, the other thing you can do is use the Harvard telescope, that thing, or use that and present your photo after.
On where?
Uh,
Uh,
the
on
Harvard
Zoom?
Smithsonian telescope, I talked about that today.
Oh, okay.
Yeah, just use that. So you can also take photos with that.
So is the class over?
Yep, it's over today. If you guys have any questions, I can put on a bouquet if you want.
Okay, thank you.
Okay.
Sure, book it.
Can't duplicate.
Okay.
The winning team get to did the winning team gets to choose the thing?
Yeah.
Okay.
So what do you guys want to play?
I want to play Pumpkin.
Okay.
Yay.
Wait, we're doing Kahoot?
We're doing a bouquet. I could find a Kahoot.
Goodbye.
Okay.
I want book it.
Okay, then we can do bouquet then. I don't really know. Here,
Winning team gets to choose.
mm, do I play Gold Quest or
Let's do something else.
what do you guys want to play?
I don't know.
Monster Brawl.
Deceptive dinos. Wait, who's from Project Coriolis?
I think they all left.
Yeah, they left.
Oh.
Okay.
Come on. I don't want to do Monster Brawl.
Okay, there.
179686.
Can you give me a link?
Yes. Okay, we'll start now. Mm. Okay, that's everything for today. Hope to see everyone tomorrow.
Bruh.